Okay guys, welcome to today's video where we're finally going to be finishing out this circuit board that goes in our battery powered T12. I know it's like been 6 months since I've touched this project, maybe more, and I also haven't gone back and looked at my old video, so I'm not really sure what I covered in that one, so we may cover some of the same stuff over again in this one. But in this one, we're finally going to finish out the ripple problem it had. I don't know if I actually showed it in that video, but the power supply was unstable and kind of oscillated a little bit. So we're going to fix that problem in this video, take a look at why it was a problem, what caused it, and then show a little bit of operation with this. We're not going to finish out the mechanical side of that. That'll be a future video, but we're going to get at least everything working so that way I can show it running and show it working with a battery pack. So let's get right to it. Okay guys, let's take a quick moment and talk about today's sponsor, JLC PCB. I've talked about them many times on the channel before, so I know you're familiar with them, but just as a reminder, they have the $2 circuit boards for 1 to 2 layers, but also you should definitely check out the fact they've added some new materials that you can use. They've added Rogers, so that way if you're working on an RF board, you can get that material you need. So definitely they are creeping into some other spaces that you may not see some of these other board houses doing. So give JLC PCB a try. Okay, for you, those of you that did not see my old video on this board, let's go for a quick little refresh of what's going on here on the circuit board. So we have a little EMI filter going on here. So your input fuse EMI filter, and then we have a buck controller. And what we're doing is we're bucking 56 volts down to 24 volts. And it's really pretty simple. One of the main things, we do have a under voltage lockout on the input side, so that way we don't drain the battery too low and damage our ego battery. And that's what this is for, is to be able to hook up to an ego battery and power one of these T12 soldering stations. Yeah, it just has these two little tiny pin headers for it, but that's because that is what these T12s are built for. So yeah, not the best connector in the world, but it's just what they're made for. So that's how it's going to work. The battery is just a screw terminal. And the issue we were having with it is that this thing oscillates. So there was possibly a design error or a layout error. And yes, definitely some of it is layout. I really should have put all of this a lot closer to the FET to kind of do that. I put it over here thinking it'd be better to be away from the magnetics for the noise and EMI that is like a broadcasted EMI instead of a conducted. I was hoping that would make it better, but really I should have had it a little bit closer there. So that is definitely a design issue there, as I should have had everything over a little bit more. But we will take a look at how to overcome that in this video. Let's take a look at the oscillation on one of these that are not modified yet. And so let's get the scope out. Here is an idea of what the oscillation looks like. So currently we have 56 volts on there, but we have no load at all. So it just kind of has some little hiccup noise there, and that's it. Pretty normal looking. But as soon as we turn on a load, so I'm going to turn a 1 amp load to it, we are oscillating, and we're oscillating at about 1.6 volts peak to peak. So that's a pretty bad oscillation there. So we definitely have a loop stability issue. So we're getting too much noise into our feedback loop over here, which is causing it to oscillate because it can't compensate in its recirculation on the FET. So it ends up oscillating. That's pretty much all is what's going on here. It's a pretty common problem you'll have with power supply design. And there's a couple of ways of handling it. You could, depending on how bad the oscillation is, you could just add more capacitance on your output and just, you know, stamp it out, and it's really not that big of a problem. I did try doing that on one of these boards here. I just put some more capacitance there. And I'd actually stacked a couple on there. I added a lot more capacitance just to see if there was an easy fix, and that really didn't help much. I also tried adding more capacitance on the input too, to see if that would help, and neither of those did do the trick for me. I also tried some different diodes here to see if a diode would fix it, but really some of the things that would have helped me in my design would have been keeping all of these components a little bit closer, and just better layout practices could have helped. But if you read the data sheet on this LM5088, 8 is the model. If you read the data sheet on there, they do mention putting a snubber across the diode because sometimes excessive ringing and spikes will cause oscillations, and even if the spikes are bad enough, they can kill it. So definitely something we want to do. So that's what I did, is add a little snubber circuit here. So what we did is add a resistor and cap from this node here. So we can just come here and draw a resistor and a cap, and then we went to this node here. So that's just about all we need to do here. If you read the data sheet, they give you a nice description of a roundabout what normally works on these. So that's going to be what we're going to do to this one. All right, so let's get this on here. We're just going to need a little bit of flux, some solder, some bus wire, and then the two resistors that we're going to stack on top of each other, just because it's what I had. So got two 18 ohm resistors and a 47 picofarad, or sorry, 470 picofarad capacitor. So yeah, let's go ahead and get these on there. I may stack a second capacitor on later just to see if that gets us a little bit better. But it's just stuff I had laying around that would make a snubber circuit that should work. So let's go ahead and get started. All right, so we have 56 volts going in, and we have 24 volts coming out. So let's take a look at the load up there. So there's the load at 24 volts. The load, I don't have the sense wire run, so when I load it, it's going to show a voltage drop, but that's really coming out of the wire. And then we have just a little bit of noise on the line there. We are looking at that at 200 millivolts per division, so it is a little more exaggerated. So let's go ahead and put a 1 amp load on it. So we'll turn it on. Like I said, the voltage drop you're seeing is not a loss of regulation. That's because this is not using the remote sense. So it's sensing at the load, not at the output. So it is 1 amp. And we can see we still have a little bit of ripple there going at about 400 millivolts peak to peak according to the scope. But let's actually do a run stop and turn that off. Go to our cursors, and we'll cursor A, and then cursor B. So yeah, our delta is 148. So we have 148 millivolts peak to peak ripple there. So that's really not that bad of ripple, especially for what we're powering here. We're powering a soldering iron. So there's really no need to go in. So the reason why our peak to peak measurement was worse was because it was catching that noise in there too, which is probably noise that if we put a filter on there, we wouldn't see at all. This should get us closer to that 400 if I do that. So yeah, that gets us closer to the 400 that the measure was using. But yeah, when measuring ripple, I prefer to use the cursors over the peak-to-peak measurements there, just because it's really more accurate. You can reject out that noise when you look at it yourself. So yeah, I'm happy at 160 millivolts. We could definitely go in and play with our feedback loop at this point and get it a little bit better. But at 160 millivolts powering a soldering iron. I'm happy. And just another one here. Our input power was 26.32 and our output power was 23.9. So we have about an efficiency of 90.8. So that is pretty efficient for a little homemade power supply here. Let's go ahead and turn on the power at the power supply. And we can see that the soldering iron boots right up and works. Let's actually verify that we can solder with it. So let's just melt some solder. And sure enough, everything works just fine. No issues. I don't know if you can see it on the screen here, but it just reads a level 23.5 volts there. Sometimes you'll see that jump a lot on the stock power supply that goes in these. It really doesn't have great regulation, but this one's not bouncing around. If we take a look at the scope, because you can see I have the scope set up there, it's going across the 24 volt rail. So looking at the scope, we can see I have the cursors already set up on it. The dips are when the soldering iron's actually running, because, you know, it's a pulse width thing. It's not always on. It has some time where it has to check the temperature, and it also just doesn't need to heat it for periods of time, especially because I'm not using it right now. So you can see that it dips down to 23.8 and its peak is 25.4. I think I actually have that cursor set high there because I know it doesn't go above 24 volts. So it's probably just the accuracy of what we're looking here. But we can see that we do have a small dip there, which would be expected because it's not directly on the power supply. There is wire coming across, but the power supply itself is not losing stability. So we have a stable power supply to run this soldering iron. So the components that would be getting hot if we had anything getting hot would be the inductor, the FET, or the buck diode, and nothing's actually getting hot. So we know we have a good design here on our power supply that should be pretty reliable, and it runs. So I'm happy with how this came out. So all what's left now for this project is the mechanical side of it, which is for mounting it on one of the Ego battery packs. I do need to get 2 pieces of metal and cut them and put them in here to be the tabs for the battery, and then this will slide right on. I've already checked it. It fits on there pretty good. So once I actually get a chance to cut out a piece of metal here, I'll do another video of this all the way together. But for now, I think this is about it for this project. It's definitely a good working power supply. It converts the 56 volts DC into 24 volts DC to run the soldering station, and it's stable, and it's not noisy. Everything seems to run good, and it's not getting hot. Well, I hope you guys learned something in this video, and I hope you found some entertainment in it. Definitely check the description below for the links on Easy EDA if you want to actually make this circuit board yourself. Maybe you want to modify it, change, you know, you could play with the feedback loop and get a little bit better. You could go ahead and integrate these the resistor and cap into the circuit board itself. So the project's there, it's open if you want to play with it. There is a link down in the description. And yeah, I laid the board out so it fits in the rails properly here. So it fits in just right. And so really, there's not a lot left to do here. It's just get this thing mounted and slap it on a battery. But yeah, I hope you guys enjoyed the video, and I'll see you in the next one.